go. Let us go over my previous lecture rapidly. And you have to answer so I know I'm not speaking into a vacuum. So have you all received the PDF copy of this lecture? The last one? Yes, no, bolo.
Yes, sir, we have received.
Okay, and who is the one who is answering? What's your name?
Sir Shashank.
Thank you, Shashank. Okay, so any questions about the last lecture? Okay, let us go through this, and you can continue to ask questions about earlier lectures even after a week or 2 weeks have passed. Yeah. Okay, so last time we introduced metric spaces. These were the objects of different categories. One can define different kinds of maps with metric spaces. So we took metric spaces and then we defined maps which were distance preserving, DP, distance preserving. That was the category of metric distance preserving. Then we took non-expanding maps, meaning they don't actually increase the distance. They may keep the distance the same or decrease it. These are the non-expanding maps. That's the metric space, the category of metric spaces with non-expanding maps. The third category that we considered was metric spaces with continuous maps. This is the most familiar category for topologists. But an analyst has to pay attention to this and many other intermediate categories which we will introduce. For example, one of the intermediate categories will be metric spaces with functions of Lipschitz condition. There is some positive constant and it puts a bound on how much you can expand. Or another category of maps which is important in analysis is metric spaces with uniformly continuous maps, not just continuous maps, but uniformly continuous maps. So the in-between categories as well, and they also have their uses. In fact, they are very important. So here was the definition, our definition of metric space, and remember we allowed it to be empty. There is no reason to avoid empty spaces, except in some theorems then you will have to say that take something non-empty, like in Baire's theorem. Today we'll look at Baire's theorem. I'll sketch a proof. So here was the definition of a distance preserving map between metric spaces modeled after a group homomorphism. A group homomorphism preserves multiplication. So then the most naive thing one can do is simply demand that distance is preserved by your metric space maps. And that is indeed a category. If two maps are distance preserving, their composite is distance preserving and identity is also distance preserving. But a distance preserving map is necessarily injective, and therefore there's severe restriction on what maps you can consider if you only restrict yourself to distance preserving maps. As you know, in mathematics, you have to deal with so many maps which are not injective. Like sin x, cos x, all such things are not injective, as you know. A polynomial is not injective, its degrees 2 or more. So next were these non-expanding maps, which was a better category. It allowed both initial and final objects. And then we talked of continuous maps. This was a very nice category, had initial objects, terminal objects. Then we talked of products. And we said that in distance preserving, there is no product if one space is non-empty and the other has 2 or more elements, there is no product. This was one of the exercises. In non-expanding maps, one can define a product, one can define a correct metric, and I had asked you which one of this is correct, but I also seem to have answered. And all of these are so-called equivalent metrics, 1, 2, 3. Is this a metric? I leave it to you to judge. And what if I put any p between 1 and infinity, etc., etc. So I don't need both the cardinalities to be greater than 2. It's enough if one of them is non-empty, let's say. Let me just make it weaker. Okay, so where was this? Oh dear. Why isn't this writing anymore? I have some problem here. Okay, and y not equal to empty. So if cardinality of x is greater than equal to 2 and if y is non-empty, then the product will not exist. So in talking about the product, whether it exists or not, we use the diagonal. Diagonal was very important. And if you put in the diagonal, if I put a Euclidean metric, then the diagonal is getting expanded by a factor of root 2. If this is 1 and this is 1, then this is root 2, and expansion is not allowed. So Euclidean metric is out, or the sum metric is out. In the sum metric, it is this plus this. You guys play chess, of course, many of you. And then, you know, a rook on the chessboard only goes horizontally and vertically. So if you want the distance between two squares on the chessboard in terms of how many steps the rook has to walk, then that metric is the sum of the two distances, horizontal and vertical. Is that clear? That's the L1 metric. Rooks, the elephant in chess, follows L1 metric. Okay. And the bishop, which goes diagonally, follows the L2 metric, you may think. Okay. So that was about the product. You may ask about the co-product. So let's get it out of the way. Exercise. Co-products do not exist in met distance preserving and met non-expanding. What is the problem with co-products? Very simple. I have a metric space X. I have another metric space Y, and I want to take the disjoint union. The problem is, how much distance should I keep between them? I can have all these points of X, and I can define the distance between them using the given metric on Y, on X, and same out Y. But between here and here, how far should they be? Somebody else may keep them very far. Somebody else may keep them closer. And now, which one of this is the true disjoint union? And obviously, there is no nice map from here to there, which is identity on X and identity on Y, because the distance is getting expanded. But then each has the same claim. And so clearly, so you make this argument precise. I explained to you the idea. The idea is you don't know how much to space the components. But this is all okay. This is okay in met continuous, because the map between here and here is definitely continuous. So what if this distance is 1 mile and this distance is 1 light year? Still the map is continuous, because nearby points go to nearby points. Convergent sequence go to convergent sequence, and so on. Here X disjoint union Y exists. So you have to give the candidate for the metric on X disjoint union. So henceforth, I will write a metric space X D simply as X.
I have a question.
When D is understood. And moreover, I will write the product X cross Y, Px, Py simply as x cross y. And I will write a coproduct Jx, Jy simply as, yeah, this is the usual notation. Okay, so now I am getting ready for my today's talk. So I did a rapid review of my last talk. And any questions about the last talk? Should we begin with new material? The new material is completeness, Baire theorem, contraction mapping. Yeah, somebody tell me.
Yeah, something
Loudly.
Can you hear me, sir?
Yes.
Yeah. When you said that, can you go slightly up? When you've talked about coproducts in metric, met DP and met NE, you have said that this will. Are you saying that this coproduct has to be the disjoint union as a set?
No. I didn't say. You will have to see that as a set. It will have to be, and then you will be faced with the problem how much distance to keep.
Okay. Can you tell me why it should be the disjoint? So I
That
thought
you have to
that
tell me. You
Sorry?
have to tell me. You have to tell me why it should be disjoint union.
Can I
Huh?
ask a question? Is there a left adjoint from sets to metric spaces?
Depends on what category of metric spaces you are talking
Met
about.
DP.
Met DP. Is there a left adjoint? I don't think there is one, but you try making one. Huh? These questions will come to later.
Okay.
So clearly you are asking more advanced questions. You already have more advanced knowledge. So I'll be happy to discuss with you, but that will take me afar because this discussion in the classroom is meant for everybody. So you should not use words like left adjoint and whatnot, which all your batchmates don't know. However, that's why I say that I am available to you after the class always or before the class. So those of you who are more advanced and want to discuss more advanced matters, please make use of my availability outside the classroom. Yeah. And in the classroom, I want to stick to quote unquote common knowledge. Okay, so let's go on to today's new material. Yeah. So I'm going to talk of something called completeness. And talking of completeness involves something called Cauchy sequence. So I'm going to introduce the idea of a Cauchy sequence. So I have sequence xi, sequence of points in a metric space X. This is a Cauchy sequence. Definition. This is a Cauchy sequence if V1 epsilon greater than 0, if there exists some n epsilon belonging to n, a natural number such that d xi xj is less than epsilon whenever I and j are greater than or equal to n epsilon. I can say 1 greater than n epsilon by changing n epsilon by n epsilon plus 1 or minus 1. Okay. Yeah, definition clear? Have I reproduced the usual definition? Yeah, all of you have seen this definition? A chorus of voices saying yes. Lagao. Let's hear the chorus.
Yes, sir.
Yes, good. I'm always afraid I might make a mistake writing such definitions.
Yes, sir.
Okay. So this is the correct definition. Very good. Now my question, immediately question. Is this definition okay in met DP? Then same question in met non-expanding, and let's put one more category, met C So more specifically, I can ask these questions. If X is isomorphic to Y and X is Cauchy, so this isomorphism, let me call F, is Cauchy, is AFS-I Cauchy? This is under an isomorphism. How about under a morphism? If X to Fy is a morphism. Not necessarily an isomorphism. Will it take a Cauchy to a Cauchy? Will isomorphisms take Cauchy to Cauchy? Will any allowed morphisms take Cauchy to Cauchy? So let's examine these questions. So if your map is distance preserving, then obviously it takes Cauchy sequence to Cauchy sequence. Agreed? If your map is non-expanding, that also takes a Cauchy sequence to a Cauchy sequence. Yeah? But a continuous map does not take Cauchy sequence to Cauchy sequence. Somebody rapidly give an example. Fails in
n 1 by n sequence and if just in
So you have to tell me what is X, what is Y, and what is F. So bolo. And what is the sequence?
X is open interval 0, 1.
Correct. X
And
equal to, let's say, 0, 1. Y equal
Y
to,
equal to R.
how about Y equal to 1 infinity?
Yes.
And Fx equal to
1 by X.
1 by X. And the Cauchy sequence is X
1 by N.
equal to, well, since we start from 0, perhaps you'll have to take n plus 1, but I don't mind. You can take n greater than equal to 0, or you can simply take xn equal to 1 upon n, taking n greater than equal to 1. Whichever way you want to parameterize your sequence, I don't mind. It doesn't make a difference. Yeah, so this is an example that shows that the notion of Cauchy sequence is not okay for metric spaces and continuous maps, but it's okay for Cauchy sequence for metric spaces and distance preserving maps. It's also okay for metric spaces and non-expanding maps. It's also okay for metric spaces and Lipschitz maps. Do all of you know what are Lipschitz maps? You encounter them in analysis. Definition.
Yes, where the distance is expanded by at most a bound.
At most a certain constant. And this is a funny spelling of Lipschitz. I don't remember the spelling, but I know there's a P in it. Somebody tell me the spelling.
SCHITZ.
SCHITZ. Okay. So I have written it. LIPSCHITZ. This Lipschitz means there exists some C greater than 0 in R such that Fx, Fy, the distance between Fx and Fy is less or equal to C times the distance between xy. So if C was 1, then you will call this a non-expanding map, right? So non-expanding maps are all Lipschitz maps, where the Lipschitz constant is taken as 1. So if F is Lipschitz, now you see that I have category metric spaces which Lipschitz maps is a category. So what will you have to check? Identity map is Lipschitz, and if I have two Lipschitz maps, their composite is again Lipschitz. Is that true? Quickly answer.
Yes, sir, it is.
Yes. So there's a category in between, right? Yeah. All right. So Lipschitz maps will preserve Cauchy sequences. Isn't that so? If F is a Lipschitz map, a Cauchy sequence will go to a Cauchy sequence. But under a continuous map, it will not. And therefore, anything depending on the notion of Cauchy sequences is well behaved for, say, Lipschitz maps or non-expanding maps or distance varying maps, but is a suspect notion for continuous maps. Okay, now let's look at one of these notions, or the important notion, which depends on Cauchy sequences, and that notion is the definition of a complete metric space. Definition. X is called complete if each Cauchy converges. Question 1. Is every convergent Cauchy? Yes or no?
No.
Yes. Yes, it is.
Huh?
Yes.
Somebody
is.
doesn't agree has to now explain. You think there's a convergent sequence which is not Cauchy?
Oh no, sorry.
Correct. So
Sorry.
every convergent is anyway Cauchy. The question is
Okay.
whether every Cauchy is convergent. Okay. The second question is there at least one complete metric space? Otherwise, what kind of definition is this? Is there at least one non-complete metric space? So what are your answers to this? These are very easy questions, so answer them very fast. Bolo.
There is
For
R.
What's the
R-
example of a complete metric space?
R.
R real
You
line.
guys are, you are working too hard. I would have given the example of a complete metric space as the
As a
empty
point.
metric space.
Yeah.
You can
Or
also
I
take
would
a
have
point.
said singleton is complete, empty
Yes.
is complete, singleton is complete. You have to give the simplest possible answers. Yeah, always. Remember, don't manufacture complicated examples when a simple example will do. Because then to prove that R is complete is hard work. So these are trivial questions, they deserve trivial answers. Okay. So is there at least one non-complete metric space? What's your answer?
Yes, sir.
Yes. Which one?
0, 1.
Open interval 0, 1.
So you have given me a non-complete metric space as open 0, 1. And then that's good enough. But how about this metric space? With mod x minus y. Yeah? This is not complete. Yeah?
Yeah.
Because I can formulate it into a sequence. 1 upon n is the nth stage of the sequence. This sequence is Cauchy because this is my metric and it's not convergent. You see, I have given you a bare bones example. There can't be a simpler example than this in some sense. Yeah. After all, you have to produce a Cauchy sequence which is not convergent. So I produced a Cauchy sequence which is not convergent, and I don't have anything superfluous. I don't have any points which are not part of that Cauchy sequence. Yeah. So I think I have made my point about how examples have to be bare bone simple, so that exactly what is involved comes out instead of all kinds of very difficult later business. Okay, so there are both complete and non-complete metric spaces, and in particular, discrete space is complete, and so on, so on, so on. Many complete spaces. So now there are 3 theorems I want to show you. One theorem is completion theorems. The second theorem is Baire. And the third theorem I want to show you is contraction mapping principle. But I'm going to show it to you rapidly under the assumption that you guys have already seen these theorems. So am I right in assuming that you have already seen these theorems at least once?
Yes, sir, but I can speak only for myself.
You can only speak for yourself, and you're the guy talking about adjoints of forgetful functors and whatnot, yeah? So
Yes,
yeah,
sir.
you should stick to speaking about yourself. Now, let some other guys also speak for themselves. You have all seen completion? That I'm sure.
Yes, sir.
Yes.
Sir, I am not.
Anybody who has not seen completion? Okay, all right, let's do completion, because after all, the way I will talk about it is likely to be somewhat different from the way your textbooks talk about it. So here's what I'll say about completion. So we will work in the category met non-expanding. I could have worked also in met Lipschitz, but met non-expanding, all this works. So I have some X. Then there exists a map in non-expanding map to a new metric space X tilde, okay, which has the following universal property. So in this pair, this is complete. So the universal property is that given any other f and any other y, such that this is also non-expanding and this is also complete. So this is non-expanding. This is also non-expanding. Then there exists a unique non-expanding map f tilde non-expanding such that this triangle commutes. Okay. Yeah, because of this universal property, Jx and x tilde is unique up to a unique isomorphism. Yeah, so those of you who had seen completion of metric spaces, yeah, you recognize this statement? Stare at it. Let's look at it the way probably your textbooks have introduced it. So let's go back, say 100 years and see how it was done. So people had a specific model of x tilde. X tilde equal to the set of all equivalence classes of Cauchy sequences xi in X with xi is equivalent to xj. So no, I shouldn't say xj, I should say yi. There are two sequences. So xi is equivalent to yi if for all epsilon greater than 0 there exists n epsilon in n such that I greater than n epsilon implies distance between xi and yi is less than epsilon. So this is an equivalence relation. This is an equivalence relation. This is an equivalence relation. And so the set of all equivalence classes I can form, and that is x tilde. And now I can define the distance on metric on x tilde by defining the distance between xi and yi. These are two Cauchy sequences, representatives of two equivalence classes. I define it to be equal to, yeah, somebody tell me.
The limit of dxi comma dyi.
dxi comma yi. Yeah, and now this limit is well defined. This is well defined. Gives a metric. Then there are more properties which you can show, that the map x to x tilde, which sends any x to the constant sequence x, constant sequence. This is the map J, and this is an isometry. You can further show that Jx is dense in x tilde. You can further show that x tilde is complete. So now let's go back and compare with this earlier definition or theorem. See, here I have defined what is completion. Completion is some metric space with some non-expanding map which has this universal property, that is completion. From this definition, you can only say that if it exists, it's unique up to unique isomorphism. But you do not know it exists. To show it exists, one method is to create one model for it. So here's the model. So the old thing that you have learned and the new formulation that I'm saying are not very independent from each other. The new formulation needs the old construction to show that there exists such a thing. While the old construction is too detailed, it has too many nuts and bolts. You know, somebody after all could have made somewhat different construction, and somebody else could have made a still different construction. You know that to make real numbers from rational numbers, you can use left Dedekind cuts, you can use right Dedekind cuts, you can use both-sided Dedekind cuts. In case your number is rational, you can decide whether to put that number itself in the left side of the cut or on the right side of the cut, and so on, so on, so on. But all these are isomorphic up to a unique isomorphism. All these are completions. So this recipe is not holy. All that matters is there is one recipe. Therefore, the question arises, if there are multiple recipes and none of them is holy, then what is the unique property which makes them all isomorphic to each other in a unique way? So there must be something abstract about them. And you want to characterize these different constructions in a simple abstract manner. And so this is the abstract manner. So this is the good thing of category theoretic formulations, that they directly go to the heart of what matters. This is what matters. And just from this much, if you just assume it exists, you can deduce all such properties, that this is dense in that, this is an isometry, all such things you can deduce just from this abstract definition. If you know existence, if you know these two together, then you can show that for anything all this is true. So at this point, I am going to ask you, do you have any questions about this so far? Clearly, you are looking at something like this for the first time, so meditate on it. But at least you know this formulation well. Am I right?
So I have a question. May I
Yes.
ask, please?
Yeah.
Yes. So can you go up to the universal property? Over there, you've not mentioned that the embedding is an isometry and a dense
It will
come from this. Okay, this is very interesting.
Yes. You see, what will happen is, you take this construction for y. Suppose for y, you take this construction we just now made. That is my y.
Yeah, but then you map via the isomorphism and say the isomorphism takes. Is that what you're saying, sir?
So if I map that as my y, and because there is such a commutative triangle and it is non-expanding, on the x part it has to be an isometry. Got it? And therefore J has to be an isometry. See, I deduced for you J is an isometry. Now your other question was, how do I show it is dense? Should I leave it to you?
Yes, I will try and then get back if I can get it.
So you see how powerful just the abstract properties, all those things are logical consequences.
Yes.
Okay.
One last thing, which is not directly related, is there a source from which, because this is very interesting and I've always wanted these kind of treatments.
You know, yeah, so this is my answer. So 1 hour before the lecture, I sat down and I said, I have to tell completion. So how will I put it now? Let me forget all these textbooks which only are now like dinosaurs. So I thought about it and this is what came out. Yeah, simple
Okay,
answer.
thank
So
you.
I have no references, but I can recommend a reference to you. It is indeed in the old standard style, but it is a wonderful book. It's by Kumaresan. It's called Topology of Metric Spaces. And it is full of all kinds of very, very useful things, very nice examples, both useful in analysis and later on in topology. So for your standard knowledge of metric spaces, I'll say look at Kumaresan.
All right.
And for the way I talk about it, the answer is I am an algebraic geometer who has worked in the Grothendieck style of algebraic geometry. And this kind of thinking is what I do for a living. And so if I want to talk about, let's say, the traffic problem in Mumbai, it might come out something like this.
Okay.
So
Okay,
now
thank you.
back to doing this. All right. So we have finished our treatment of the first one of this completion. Oh dear, that's terrible. Okay. Now let's come to Baire's theorem. And I'm going to give a pictorial proof of Baire's theorem because it's very difficult to remember all the numbers, how you arrange. Okay. So here's what Baire's theorem says. I think I stated it earlier. Bayes theorem, and it says let X be a non-empty complete metric space. Okay. Let Xi, well, perhaps I shouldn't call them Xi. Too many X's will start making the thing rather. Okay. Let Yi I equal to 0, 1, 2, whatever, be a sequence of nowhere dense subsets of X. Okay. Then union for I of the Yi is not equal to X. This is called the Baire category theorem sometimes because of the word category used in some other sense in some earlier usage. Okay, have you guys seen this statement? Do you recall it? Let me show you 1 or 2 applications. Here's an application. So real numbers, as you know, and it's a difficult theorem, or it's
Hello.
hello, yeah.
Yeah,
Somebody wants to
sir.
talk?
I haven't seen in this format. Then union I is yi is not equal to x. I have seen in some.
Union, I should say closure, yeah.
Uh,
In what format have you seen it?
the I think I have seen in some in terms of intersection. I guess.
See, the complements of yi's are, and then the complement will union becomes intersection. You can rephrase Baire's theorem in terms of the complementary sets. That's also possible. So if you look at Kumaresan's book, you will find various alternative formulations. And he'll begin by showing that they are equivalent before proving them. Yeah? Yeah. So once you understand it, you also understand those other things. So let me show you some applications of this. So you know the real numbers are complete. In fact, you take completion of rational numbers to form real numbers. So suppose a real numbers is your complete metric space. You know it is non-empty. And therefore, this shows that real numbers are not countable, because if yi's are singleton points are nowhere dense, and therefore the union of these singleton subsets can never be all of real numbers. So real numbers is uncountable. We proved it so easily by this Baire theorem. So let me give you another application. All of you have seen this Hilbert space L2, right? L2 of sequences, square summable sequences, infinite square summable sequences, small L2. Yeah, you have all seen it? Small L2, Hilbert space of square summable sequences of real numbers or complex numbers. Let me write it here. In case you have not seen, here's an A. So let me list the applications. Application 1. R is uncountable. So now I'm going to list the second application. There is this L2R. Vector space. This vector space has all such sequences, x0, x1. These are all real numbers, such that sigma xi square is less than infinity. And you know, this is made a metric space. In fact, on this, there's a norm. Norm of this is this sigma xi square. And then the distance is defined as the norm of the difference between two vectors. So this is a complete metric space. Okay, so for this one, what I'm saying is its dimension as a vector space is uncountable. Because suppose its dimension was countable, then you take a basis. Suppose suppose not. If not, let E1, E2, blah 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 be a basis. And now you take the sequence of subspaces. Y1 equal to the vector space generated by E1. Y2 as the vector subspace generated by E1 and E2. And so on. These are nowhere dense. By the way, what does nowhere dense mean? I never asked you whether you guys know the word nowhere dense. Nowhere dense. Y containing X is nowhere dense. Means interior of the closure of Y is empty. There is no point in the interior of the closure of Y. That is what is meant by nowhere dense. Now all these are already closed and they are nowhere dense, and so their union can never be this, but if this was indeed a basis, then any vector is a finite linear combination of these vectors, so it will lie in one of the large enough Yn, so that all the non-zero coefficients are up to the stage n. Yeah, is this application clear? And there are any number of applications in analysis. So this Baire category theorem is very, very important. Now I am going to show a quick proof by pictures. So here's a picture. So I take Y1, and because Y1 closure is therefore not equal to X, otherwise Y1 will be everywhere dense. So I can take a point. Yeah. What's the opinion?
Sir,
Yeah.
sir, actually for 10 to 20 seconds, my network is lost. So can you please explain the last 10 to 20 seconds?
So I said that I'm now going to show you a proof of Baire category theorem, and that took about 5-6 seconds. And before that, I explained the proof of how this L2 is uncountable dimensional as a vector space. And then I said there are lots of applications of Baire's theorem in analysis. It's very important. Okay. So now let's get back. So I'm going to show you a proof of Baire's theorem by drawing pictures. Go read in Kumaration's book and you will back up these, but you should be able to fill in the words. So there is y1 bar, and y1 bar is not equal to x, so this may be y1 bar. And so now there's a point x1 which is outside. So there's a ball. There's a ball, let's say, of radius r. B x1 r intersection y1 bar equal to empty. So now take half the ball. Take half the ball around it. Its radius is r by 2. And this ball cannot be contained in y2 closure. Right? Because if there was such a ball in y2 closure, if this ball at around x1 with radius r by 2 is not contained in y2 closure, y2 closure has non-empty interior. Therefore, there is a point inside it, x2. There is x2 belonging to the ball x1 r by 2 minus y2 closure. Now I take this point x2 and I take an even tiny ball around it. I take its radius to be r by 4. I take the ball around x2 with radius r by 4. And now I choose something in it which is not in y3 closure. And I keep doing it. This is what I go on repeating. And by repeating this, I produce a sequence x1, x2, x3 sequence. This is a Cauchy sequence in X. Therefore, convergent as X is complete. So let's see where we use the hypothesis. I said this is not equal to this. Such a thing won't be possible if it were empty. Yeah, there won't be any such point outside and whatnot. So I have to begin with something non-empty. Otherwise, as you can see, the theorem itself is false. So in order to have points to argue with, I need X to be non-empty. And for the points so created that sequence to converge, I need X to be complete. So I have the limit of Xn equal to, let's call it X infinity. Then X infinity does not belong to any of the yi's by construction. The way we constructed it, it does not belong to yi for each y, for any y, and therefore union yi not equal to x. This is the proof. Proof is very easy. You only have to check the inequality that it is indeed Cauchy, and that is clear the way we have chosen points to be closer and closer and closer by choosing them in smaller and smaller and smaller neighborhoods, which are inside the earlier smaller and smaller neighborhoods. And every time the radius becoming half of what it was, or less. So distance is half or less every time. And so that is why you get a Cauchy sequence. Simply by the basic idea that 1/2 plus 1/4 plus 1/8 plus 1/16 blah blah is a convergent sequence. That lies at the heart of all this being Cauchy. Yeah, you get the idea? See, this is what is required now, that when somebody explains a proof like this in terms of pictures and the idea, you should be able to convert that into a written version. So exercise, write a proof. Write a proof and without pictures. A picture is not a proof. Okay. Now let's come to, as usual, I run out of time very, very rapidly. So I said in this lecture, I'm going to show you some things about metric spaces. And that last thing is contraction mapping. So here's the statement about contraction mapping. First, a definition. Definition: f x to y is called a contraction mapping if there exists some 0 less than equal to c strictly less than 1, such that for all x1, x2 in X, d of fx1, fx2 is less than or equal to c times the distance between x1 and x2. So in other words, this is Lipschitz with c less than 1. This is what is a contraction mapping. It's a Lipschitz mapping where that Lipschitz constant is less than 1. Yeah, this is called a contraction mapping. And now, the result about contraction mapping says that theorem, and I think this theorem is due to Cauchy, but I may be wrong. So you look up in books to whom this theorem is. Theorem. Let X be a non-empty complete metric space. Let f x to x be a contraction mapping. Then f has a what is called as fixed point. That is some x belonging to x such that fx equal to x. Moreover, the fixed point is unique. There are no two fixed points. Of course, that's obvious. If fx was x and fy was y, then the distance between fx and fy has to be strictly less than the distance between x and y if it was positive. But if both sides are 0, then this is okay. So you are forced to that the distance has to be 0 if this is to be satisfied. So if it exists, then obviously it is unique. But why does it exist? So you see here again, we have to say non-empty. So you would get the idea that I showed you things which assert the existence of a point. If some theorems assert the existence of a point, and if you begin with an empty metric space, that's not going to work. Somewhere then you have to assume that there's a point. Therefore, in these theorems exactly, you have to say that let me have a non-empty complete metric space. Okay. So let's prove it. So idea is very simple. You start with an arbitrary point x0. Arbitrary. Exists as x not equal to empty space. So you see, the use of non-empty is very transparent where it takes place. Now let xn plus 1 equal to f of xn. So keep iterating this. So from x0 you make x1, from x1 you make x2, and therefore you get a sequence x0, x1, x2. Okay. Exercise. Prove that xn is Cauchy. And this uses contraction mapping. That Because this is a contraction mapping, this uses that F is a contraction mapping. This uses that F is a contraction mapping. Otherwise, in an arbitrary metric space, even if it's non-empty and complete, and I take some arbitrary self-map and keep applying it to itself, I don't get a Cauchy sequence. So this is why it is Cauchy. Next, as X is complete, this sequence converges. So let X infinity equal to limit of Xn. And now prove that f x infinity is x infinity. So I've broken down the proof for you in tiny steps, and your job is to fill in those tiny steps. Okay? And this as a PDF file is going to come to you in half an hour or less, whatever time it takes for me to save it as PDF and email it, and for your organizers to email it to you or WhatsApp it, whatever. Soon you'll have all this in your hands. So is this proof clear? Contraction mapping principle. Any questions on this? I should mention application. The most important application of this is to prove Cauchy's existence theorem for ordinary differential equations, one of the foundational theorems of analysis, that first order differential equations of certain kind, dy by dx equal to fxy kind of differential equations, have a solution, a unique solution under whatever appropriate hypothesis. And that comes from Lefschetz fixed point theorem. I think, and correct me if I am wrong, the Simmons book indeed gives this proof of existence of a solution for a differential equation. Does it? Those of you who have the book should be able to tell me. Hello, hello, have I lost all you guys? Is anybody there?
Yes, sir.
Yes, sir, which means you are there. Okay, so you remember seeing existence theorem for ordinary differential equations? Okay, perhaps it's in another book of Simmons. Have you guys seen a book by Simmons called Differential Equations?
Yes, I know
yes,
one.
Probably that book, but I think even the topology book has this, but I'm not sure. So even that book has a proof of the existence theorem for ordinary differential equations using this fixed point theorem. Am I right? Okay. Now I have only 1 minute left, so I will ask you, there are complete metric spaces. I asked you for trivial examples. Now give me some important example of complete metric spaces. So let me give you very important example of a complete metric space. Important example. Of a complete metric space in analysis. So should I say important examples? So there are Hilbert spaces and Banach spaces. Okay, these are the important kind of examples. Oh, what happened? It just disappeared. Where are we? There. So BANACH, Banach spaces. The color changed. Wow. And in particular, I want to show you one particular example. How about this C01? continuous functions f. So this is a set of continuous functions f from 0, 1 into R with sup norm, which means uniform convergence. Convergence is uniform convergence. This uniform convergence leads to completeness. If I have a sequence of continuous functions converging uniformly to some other function, that other function is also continuous. Yeah, you have seen this. So this is the important example of complete metric space. Okay, so that is it for today. I have run out of time, and so any questions? I am going to be here till so let me go to, yeah. So ask me if there are any questions. Go ahead. Just give me a moment.